Laura. Welcome everyone to today. We're going to have about half an hour to 45 minutes, just a little discussion about mixing equipment and what Ansys has to offer with regards to that. So hopefully you can all see my screen and I will get started on the webinar. All right, so we are looking at mixing equipment, and so the challenges in mixing industries. So the main design goals is obviously efficient and cost-effective mixing processes to bring quality products to market in less time. And it is very common in upstream processes in mining, water treatment, chemical, pharmaceuticals, biopharma, consumer goods, and food industries, amongst many other different things. So it is a very important part in a number of processes to keep an economy going. So with the design requirements that are required for the mixing industry is often a scale up various unit operations from lab to plant scale, and also adapting various size operations units at different plants or different geographical positions. So also adapt existing equipment to new formulations. So if you're changing your ingredients, you need to adapt accordingly, and ensure plant operations and meet government regulations. And then obviously the most important is to ensure your batch quality consistency through digitization. Okay, so the quantified impact on simulation on efficient mixing equipment. So the efficiency, you can improve efficiency by 5 times or 12% reduction in power. That is from a few clients that we have dealt with. Then also production time reduction. So reduction in the cultural development time. So you don't have to spend as much time developing the product and optimizing the product. If you're using simulation, you can make that process a lot smoother and make it a lot quicker as well. And then obviously revenue. So an increase in concentration of your product can add millions of dollars of revenue per batch. So it can definitely improve your revenue throughout the life of your equipment. Okay, so what do we do? So Ansys has a number of different ways that we can deal with mixing equipment, and I'll go through a number of different ones and look at what is the common goals, the engineering challenges, and what we have to offer to solve these particular problems. So the most common, most simple approach would be a single phase mixing system. Generally, the goals of something like this would be the potential scale-up issues to be just identified for risk analysis, the impact on the geometry on product quality along the lines, the impact of operation conditions that affect the unit operation, and then obviously retrofitting new processes or new parts to the equipment and ensuring that it still meets requirements. So the engineering challenges we have with generally we're scaling up and scaling down equipment. It may be different at different geological positions, and obviously the batch sizing and things like that. So important things that we need to look at is the residence time and blend times. Obviously we want to optimize that and minimize those as much as possible. And then in shear exposure, if you want to know if your material is undergoing any excessive shearing, and that may affect the quality of your product. And then obviously blending of non-Newtonian fluids can be a challenge in itself. So what does Ansys have to offer in terms of the single phase mixing system? So we can perform a steady state or transient analysis. It doesn't have to be just a single species, but it will be one single phase, but it can be multiple species with different material properties. Then we can also look at particulate flow and DPM, discrete phase particles, and we can see how they interact with our different phases. And then we can look at obviously complex rheology and complex flows within the system, and we can look at multi-phase, multi-particles and things like that. So the solutions that we have, obviously we have a easy to use parametric geometry, which allows geometry scaling from lab scale to production scale. And then we can also use designs of experiments within Workbench and ANSYS to find an optimal operating point for your specific design. Okay, so the common outputs that we can get from a single mixing, so we can see flow field visualizations. We can see if there's the residence time, blending time. We can see if there's adequate mixing or areas where there's not good mixing. And then we can also look at shear rate tracking and reporting to see if the material's thickening because of shear stresses and things like that. And then there is obviously quantitative and qualitative reports, contour plots, flow visualizations, and things like that. So the benefits that these can bring to us, so to understand the mixing characteristics on a plant scale, how long to mix to get a desired quality, and this can be scaled up and scaled down without us doing physical tests. We can do this, these simulations, and get answer these questions for us quite quickly. Okay, then the equipment sizing, can we use the existing vessels? Can we enlarge? Can we have bigger scales and things like that? And then obviously the save expensive raw material usage in the testing process. So often these equipments are large and expensive to manufacture, and we do not want to have to waste unnecessary materials building these testing facilities. Okay, then gas liquid filled systems, so filling and mixing. This used to be quite a difficult problem to solve, but it has become a lot easier in the later editions. So again, what are the customer's goals? So to reduce time to market by scaling up and scaling down, increasing yield and productivity, and then predict failure modes. So lack of mixing, is there gas entrainment and things like that. So the engineering challenges are generally do we scale up? Can we scale up or scale down? Is there gas holdup in the system? Is there prevention of gas short circuiting in the system? We can also predict mass transfer and then predict vortex formation. And then we can also limit shear rates and see if there's how the viscosity changes with time. So with the gas liquid systems, we can perform this again with steady state as well with transient. Most likely it will be a transient analysis if you're doing things like filling up and emptying and mixing. It most likely a transient behavior, but then we can have multi-flows, so multi components, so multi-phase. So we can have a liquid as well as we can have a gas phase, and we can monitor how those two interact. So the solution is for accuracy, for flow patterns and turbulence. Then we can do advanced modeling of gas and liquid without reactions. And then obviously we can still use designs of experiments to find optimal operating conditions. So we can see the interaction between the gas and the liquid phases in this particular example. Okay, so our output for a liquid gas system, we can again visualize our flow fields. We can visualize our liquid and gas fields separately, and we can see also the interaction of them. We can look at bubble resilience time prediction and bubble size distribution, and then we can also look at mass transfer and then shear rate predictions and reporting. The benefits obviously understand mixing characteristics, flow visualization, residence and blend times, as well as vortex sizes. And then we can predict the shear rate and shear history of our product as mixing occurs. Another example of a gas liquid system is some form of bioreactor, where we actually have additional reactions occurring. So the customer goals is cell cultures could take many hours to weeks to scale up. And we want to maximize our yields per batch, and we'll avoid batch failures and hence wastage of costly APIs, active pharma ingredients. So the engineering challenges are very similar to the gas liquid system, same as scaling up and the gas holdup and prevention of gas short circuiting and limiting of shell life. So the capabilities that we have offer here, we can solve steady and transient. We can have multiple flows, multiple phases, and we can have complex flows. The prediction of the gas distribution and bubble size with the population balance model, which can be done to better predict the gas and bubble distribution, and then heterogeneous reactions to show oxygen concentration in a sparge tank. So we can do reactions as well and see how those affect our product. So with the reactors, we can also visualize our fields, our different phases and our gases and liquid phases. We can look at our bubbles and the size distribution and the times of those size distribution of those bubbles. And then we can look at mass transfer and the shear rate predicting. So the benefits of living cells which produce pharmaceuticals must breathe gas holdup interface area, so we can maximize the mass transfer, and then we can predict the blend time and predict the shear rate and the shear history as well. The next thing we can look at is solid suspension, which is a very common thing in water treatment and other things like that. And so we need to ensure adequate solid suspension in tanks, and we can ensure that there's dissolution and crystallization systems are working, and the minimum power requirements, so longer impeller and vessel life required. Okay, so the engineering challenges, once again, is are we able to scale up and scale down these things? We need to find solid suspension and cloud height predictions, and then dissolution systems as well as crystal growth. So the capabilities we have to offer steady state and transient, there's multi-species and particulate flow, DPM and things like that. Then you can also have complex chemical reactions and complex fluid flows. So the solution gives us accurate flow patterns and turbulence, and advanced modeling of solid liquid mixing along with reaction and drag models can be performed, and the design of experiments can be used to find optimal positions, operating conditions. With the solid suspension, we can visualize our flow fields. We can also visualize our cloud height and measure that quantitatively. Then we can look at the dissolution mass transfer as well as the rates of dissolution, and then we can predict the growth of crystals. So the benefits, we understand the flow characteristics, the solids distribution, the cloud heights, and we can predict the shear rates, and then we can minimize batch failures. Another type of mixer that can be solved in ANSYS, and that is intermeshing mixers. So that is actually moving geometry or moving meshes, and we want to be able to reduce time to markets. Obviously, we want to increase the yield and productivity and predict failure modes before they occur. So the challenge is, again, can we scale up and scale down? What kind of residence times and blend times do we get? Are we exposing our material to excessive shear rates? And are we blending non-Newtonian fluids and things? And then obviously what makes this different to any other of the previous mixes that we looked at was the complex motion of using a moving mesh rather than just a moving reference frame, which is often used. Yeah, so with intermatching mixers, you can do transient, you can do multi-species, multi-phase, you can do DPM, and you can have complex rheology. The Fluent will ANSYS handles the intermeshing regions and handling of small gaps and things like that very well. So you can get advanced flow patterns and shears and temperatures within your geometry. You can have a very advanced modeling with multi-species, and then you can use design of the experiments to optimally find your operating conditions. So what are the outputs? Well, we can verify the motion visually based on the inputs that we define. Then we can also look at the flow visualization and distribution of the mixing, residence time, blending times, and then shear tracking as well. Then obviously quantitative and qualitative reports like images and values of interest that we may want to look at. So the benefits, we can verify the blade motion, as I've mentioned. We can look at the distribution of the mixing and the residence time, and we can look at the shear field dispersive mixing. Okay, the next thing is a static mixer. Something that's not as common, but something, for example, a thermal mixer, something needs to mix two different fluid temperatures efficiently. So we can look at the customer goals in that. Obviously, we want sufficient mixing and we want to be able to size our equipment correctly. We want to find out what kind of pumping power we require and what pressure drop we get through our system. And then we can look at viscous heating and obviously the temperature control based on those parameters. Yeah, so we can look at complex geometry. We can do parametric definition and run parametric studies. You can do complex rheology as well as multi-species. And if necessary, you could do multi-phase as well. The solutions offer accurate flow patterns, shears, and temperatures, and you can use advanced modeling for complex rheology, customized geometries, and multi-species. So the benefits of it, you can determine the concentration variance throughout. You can also look at residence time, shear tracking, local temperature variations. You can look at it on the larger scale, the pressure drop through the system so that you can predict what kind of pumping power you require. And then you can use detailed interaction with upstream and downstream elements. Okay, then the last thing is cleaning in place. With a lot of systems that we require nowadays, require cleaning in place to simplify and to make the cleaning a lot easier. So we need sufficient and consistent cleaning processes, and the system size needs to be, we need to be able to apply this regardless of the system size and make sure it works sufficiently. So obviously our challenge is to minimize the cleaning time and minimize the agents that are used to do the cleaning, and then these cleaning agents need to be pumped through the system so to minimize the power consumption while the cleaning occurs. With this, we can do single and multi-phase modeling such as VOF and discrete phase. We can do the solution offers free surface and droplet formation tracking models. You can predict jet throw and a liquid film formation as well. So the outputs, it gives you a cleaning jet range, a cleaning impact pressure and shear forces, and time to complete the cleaning process, and then also the liquid and liquid consumption. So you can find the benefits of it is you can determine the effects of the nozzle's head selection, the time it would take to clean, the consumption, and then obviously the film coverage. Okay, so once we've done those on a model simulation level, we can look at often something on a system level as well. And ANSYS has a number of things that help you use a system level approach to designing and finding solutions for your problems. So the quick and right decisions are process parameters for operators across geographies and time zones. So the engineering challenges is the use of CFD by non-experts, because we don't want to have to have every time we want an answer, we don't want to have a CFD engineer using it. We would preferably be any other person suitable. So internal processes requiring 3D CFD simulation by plant operators. We can coupling 3D physics with 0D systems models, and then it helps with operator training as well as digital commissioning of equipment. So the capabilities, we have a reduced order model generation and consumption, and we have digital twin capacities. So the solution is there's a template wizard for easy to use templates that remove the burden of having to be a simulation expert. There's a template on Cloud and Manera, and reduced order models can be consumed by plant operators for quick analysis. So the output automatically creates of 3D CFD simulations, geometry, pre-processing, setup and reporting, and a lightweight ROM representing equipment for real-time use by plant operators on light hardware. Digital twin for online and offline use. And the benefits, obviously, of the system simulation of line manufacturing plants can help in digital commissioning and operating training. And then the template requires no training and experience, and it is a very useful tool. Okay, so that pretty much sums up my presentation. There is a dedicated mixing answers on Learning Hub if you want to look at that. So yeah, that's it in terms of the presentation. I'm going to just show you a quick demo of how you can go from Fluent or a mixer, and then taking that to some other software to do additional analysis, for example, something like a structural analysis. Okay, so I'll quickly run through this. I've set up this on in Workbench. So we have a geometry for the fluid region, then we have our Fluent setup, and that Fluent is transferring data to the setup of our static structural. And then we have a geometry for the structural. Okay, so I want to just first open the fluids and show you the basics of setting up a mixing problem. And I'm just going to give you a walkthrough of this. Just give me a moment while it opens. Okay, so this is open. It is open up in SpaceClaim now. So I have two groups here. I have a fluids, which is my fluids group, and I have my baffles. My baffles are just surfaces in there, and then in my fluids, I have a body with subtracting where my rotating regions or where my impellers are. And then I include two rotating regions with the cutout of the impeller inside. So you can see the impellers there. And then, so that's the basics of it. You need, for most, if you're doing moving reference frame, you need a cylinder. Even if you're doing mesh motion, to be honest, you need some form of cylinder here around your impeller to show where that is going to be, what is going to be moving. Then another important thing within SpaceClaim is to create name selections. I've created a number of name selections. For example, I selected that body and created a name selection fluid moving reference frame 1. I did the same for the top one. Then I put walls on the baffles. Just note, if you are dealing with surfaces and you want to have them as baffles or something like that, don't select the body. Ensure that your name selections are on the faces rather than, so if you select that, you select the face and not selecting. It will, if I no, it's not. If I were to select the surface itself, it would say one body, but I want to select the face, and then it works correctly when going to Fluent Mesher. Then other things, I've just added walls on my name selections to my impeller walls, to the shafts, And then I've just given them names accordingly. So that's how I've set it up. That's the geometry side. I have walls for the names for the tanks, as well as the top of the tank and all of that. So that's how the geometry on the fluid side is set up. Then on the structural side, we don't need a fluid region. We only need the impeller. So again, that's why I've got two separate geometries. They should be in the same location so that we can transfer data accurately, but there will be different geometry, where on the fluid side, we would need the fluid regions, and on the solid side, on the structural side, we need the solid regions. So here is the impeller on the structural side. I've split it up. I've also added name selections so that I can map my data. So these were the same as the name selections I used in my fluids, just so that obviously they're on the structures now, so that I know where to transfer data from what name selection to what name selection. Okay, so then I'll just quickly show you, run through the setup on the Fluent side. So let's go to the Fluent meshing. Just going to open the Fluent meshing side of things. Okay, so the first thing you would do is just import the geometry, just make sure the units that are being used. I then added a face sizing to the impellers of the walls, added to the impellers of the walls. Then I created a mesh. I put a minimum size of 1 mil, maximum size of 20 mils. Obviously, that would depend on the scale of your geometry, but that's gives you a good idea. And then I just added cells per gap of 3 between faces and edges. Then I describe my geometry as both fluid and solid regions and or voids, and then I switch all the others. Sorry, I did ensure there was shared topology in Workbench, in SpaceClaim before I brought this mesh in. Then I updated, these were the internals. They were just the faces of the rotation region, which I've named, and they are internal, and then the rest are walls. This could be, if I wanted it, I could take that to a pressure boundary if needed. Then I specified the number of fluids. It specified my regions. I defined them all as fluids. I specified a smooth transition boundary layer of 5 layers thick, and then I generated the mesh using a polyhex for mesh. And then the last step was to create an improved mesh by right-clicking on this and saying improved mesh. Then it improved the mesh because it was less than 1.0.15, and now it has improved it. And then we can see what the cells look like. So you can see we have a finer grid on the impeller blades, and of course a grid everywhere else. Okay, then we can switch to the solution mode. And when we go to solution mode, we'll set up a couple of parameters. Okay, then I would go to the setup. I'm just clicking on the solution because otherwise I'm going to erase my solution. So I'm just clicking on the setup. It will show, I'll still show you my setup that I used. Yeah, just give it a couple moments to open. Okay, so let me show you the basics of what I've done. So under physics, I went to my operating conditions. I specified a gravity in the y direction, just ensure that is correct. And if you want an operating density to calculate pressure gradients at boundaries. Then I switched on species transport because I have multiple species. I used the general, just use any mixture library and then edit it thereafter, and I specified 2 species. Well, it specified 2 species. Then the next thing I did, it was go to my mixture, and I edited my mixture. And then I went to my names, and then I added the different mixtures. So if you look in the fluids, should I say, I added a slurry liquid with a density of 1,200, viscosity of 0.01, etc., etc. And then I did a water liquid as well. And then I used those 2 liquids in my species mixture model, and I used for density, I used volume weighted, viscosity mass weighted, and mass diffusivity, I used kinetic theory. Then the next thing to do once completing your materials is to define your moving reference frame. So under your cell zones, you should have your name of the moving reference frame. I have it. There's the name I gave it. I then turn frame motion on. I specify my rotation axis about the y-axis, and I define a rotational speed. I do that for my second region as well, and then make sure there's frame motion. If you're doing mesh motion, this is where you would also switch it on, but we're doing just frame motion, which is sufficient in most cases. Okay, then the next thing is on the walls. So the baffles we don't need to worry about, but on the walls of the impellers and the shaft, I'm going to right click and multi-edit them. You can edit more than one item at once and then I've specified it as a moving wall. It's absolute rotation, and I specified its rotational axis, and I gave it a rotational speed. Okay, and then that's it. Then I added, then in the methods, I just had it as coupled. You can use default settings, play around with these, but use defaults, and if necessary, you change them. But I use coupled. You can use what is, but defaults are generally the best ones to use. Okay, then the last thing I did before solving was set up a couple report definitions. So I wrote, for example, created the average velocity within my system. So I looked at the average velocity. I also added a few like maximum velocities, standard deviations on my slurry, things like that. And then you can add monitors and plots to that as well. Then the next thing I did was create a cell register. So I created a volume. If you're not too sure, you can check under the scale, and that gives you your domain dimensions and your extremes on your domain. And then you can use that to create it. So I just created it up to halfway. So it's the halfway of the tank, and I created a cell register. Then the next thing to do is initialize. So you click initialize. I use standard initialization because I want initial conditions, because I'm going to be doing a transient analysis. And then I patch thereafter, and I specify my liquid slurry, and I use the patch region, the register that I created, and I'm patching it to 1. Okay, and then I'll create some animations, or it's always good to save your data. So I save it every 100 iterations and only every 5. Then it's good to add a couple contours in that. So I added, here's For example, the contour of the mass fraction of slurry at the beginning. So you can see it's halfway up slurry, half water, and then it mixes accordingly. Okay, so that's the basic setup of the fluid sides. The only other thing you would need to do is specify a time step and number of things, and then you would click solve and allow that to solve a number of iterations until you have reached a converged solution and you're happy with the results. Okay, so once that's done, you just need to either specify that your solution is up to date, even if it's not just specify it's up to date. Then you update this, open this model and setup, and you also update or make sure the solution is updated, and you update this setup. I'll show you the setup on the mechanical side. I'm nearly done, and then I'll show you the final results. Okay, so on the mechanical side, I added a few mesh regions. So I split my geometry up also to help me make create a better mesh. So I create sweeps there, tetrahedrals there, and sweeps on all my other geometry. And then it creates a decent mesh, which you can see. So it's a nice sweep on my geometry. So again, I'm using shared topology. So you can see there is definitely shared topology. And that's why I needed to put a tetrahedral for this one. Okay, once that's done, you can then add your fixed support. For example, I added a fixed support at the top on that surface, and then I imported the loads. These imported loads should be there as soon as you've updated the setup. Then you just go insert, and for example, I'm going to say pressure. Then I'm going to select the pressure. Then I'm going to select the name selection. I select the wall as shaft, and then I ensure the CFD surface has the same name selection. And I kept them consistent between models so that it would be easier to work with this. And then once you've imported all your geometry, you can solve this, and you can then get your answers. So you can look at total deformation, you can look at stresses and things like that. And that's very easily being able to transfer your results from CFD to a mechanical. And there's a number of different physics that we can do, and ANSYS streamlines most of them. Yeah, so that is that from my side. I hope you all enjoyed it. I hope you found it hope you found it interesting. If you have any questions, feel free to ask them. I'm going to stop sharing my screen, but yeah, I hope you enjoy the rest of your day and weekend further.
Thanks a lot for that, Keith. I think it was very useful and valuable for a lot of us. Is there any questions from the audience at this stage? Keith, I think that's it then. There's no questions. So what we'll do, we'll send the recording to everybody. And then if there's any questions afterwards, we can just answer them.